right. There we go. Okay, question number 17. This is the last problem that I showed you at the end of the last lecture, and I said it was the first thing we were going to do today. So I'm going to keep this promise. It says at 60 degrees Celsius, the kW of water is different than it is at 25 degrees Celsius, right? At 25 degrees Celsius, kW is 1 times 10 to the minus 14, but now it's 1 times 10 to the minus 13. What is the pH, pOH, concentration of hydronium, and concentration of hydroxide in water at 60 degrees Celsius? Well, let's take the same old approach here that we did last class. If you didn't quite follow me all the way, I said, well, if you have two water molecules and they undergo autoionization, right, which is something we discussed last class, so that you end up with a molecule of hydronium, which is aqueous, plus a molecule of hydroxide, which is aqueous. Well, we know that initially water has no concentration to speak of. And if we have none of these, if we have 0 molar of this and 0 molar of this, we know that there's going to be a change. It doesn't affect the concentration of water, but we're going to get some hydronium and we're going to get some hydroxide. Since the ratio of hydronium to hydroxide is 1 to 1, we're going to get the same amount of each. And so at equilibrium, again, concentration of water is no concern to us at all, but we're going to have the same concentration for both of these. And so we can say that our kW, which is equal to the concentration of hydronium times the concentration of hydroxide, right? That's a formula we learned last class, and you can also just derive it from this equation, okay, is equal to x squared, which is equal to 1.0 times 10 to the negative 13. And so x, which is equal to the concentration of hydronium, it's also equal to the concentration of hydroxide, is equal to, and I'll do it over here, x is equal to the square root of 1.0 times 10 to the negative 13. And so when you punch that into your calculator, you get that these concentrations are equal to 3.2 times 10 to the negative 7 molar. So that answers the first part, the concentration of the water and the concentration of the hydroxide. Now, if we want to calculate the pH, pH is equal to minus log times the concentration of the water, the hydronium, which is 3.2 times 10 to the negative 7. Since I have two significant figures in my concentration, I'll report my pH to 2 sig figs, which is going to be equal to 6.50. And for my pOH, rather, I'm going to get the same thing because the concentration is identical. So my pOH is going to be equal to 3.2 times, sorry, Mr. Dion's thinking too far ahead, is equal to 6.50. And so you can see how the change in temperature not only affects our equilibrium constant, but it affects the concentration of the hydronium and the hydroxide, okay? And it lowers the pH and it lowers the pOH as well. All right, so we end up with a different scale of pH at 60 degrees Celsius than we do at 25 degrees Celsius. All right, there we go. Well, let's move on from there. And I have a bunch of these different slides here that talk about, some interesting tidbits about acids and bases. This one comes directly from our textbook. I have the caption written down here at the bottom. It says the pH and the pOH scales represent concentrations of hydronium and hydroxide respectively. The pH and pOH of some common substances are shown in this chart. Look, except for calculating pOH like directly, we don't refer to pOH a whole heck of a lot in general chemistry too. If you were maybe an analytical chemist, you might talk in pOH terms sometimes, but generally speaking in this class, we'll be talking about pH. So if you can start from pOH, and again, the pH scale goes from exceeds 0 to 14. You can have a pH below 0, right? You can have a pH greater than 14. But anyhow, you have things that are really acidic, like a strong acid, like hydrochloric acid. What's a really strong base? Sodium hydroxide. That's a very strong base. Okay. What about something that's neutral, like water? Blood has a pH of around 7.35. And all you biochem people can probably tell me exactly what it is, but I think it's around 7.35 to 7.45. And there's blood has a really interesting capability to neutralize acid or base that's added to blood, and it's able to maintain that pH range, that narrow pH range of blood, and we call that a buffering capability. So we say that blood is a buffer. Now, some of you have studied chemistry in high school. You might have been introduced to the concept of buffers, and we'll look at those next week. Anyhow, what about a weak acid, right? I told you that acetic acid, which is essentially vinegar, right? That's a weak acid. Well, look, that's got a pH of around 2. And what about something like an antacid, right? Something that you would use to neutralize stomach acid, like milk of magnesia, which is essentially magnesium hydroxide, right? It's a base, but it's not as strong as something like sodium hydroxide. Okay? Anyhow, we could talk about that all day, but let's move on from there. You've got to know the strong acids. There are 6 strong acids that you have to be familiar with, and 6 strong bases that you've got to be familiar with. Okay? Meaning, you've got to have these acids memorized. Hydrochloric acid, hydrobromic acid, hydroiodic acid, perchloric acid, nitric acid, and sulfuric acid. Those are the strong acids. You've got to have some strong bases memorized. Okay? Strong bases are lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. You see that magnesium hydroxide isn't on this list, right? It's not as strong as something like sodium hydroxide, okay? And there's no way for me to get around this other than to tell you that you have to memorize this, okay? You have to memorize the list of strong acids and the list of strong bases. Now, when it says here that strong acids react essentially completely with water, what does that mean? That means if you take an acid like hydrochloric acid and you put it in water, you don't put equilibrium arrows. It's not an equilibrium. It's going to react completely with water. So we draw an irreversible arrow, and we would end up producing hydronium plus the chloride ion. The same thing is true for the bases. Now, we don't draw or write a reaction between the base and water, so to speak. You could technically, but the way that we would represent that a base is strong is if we had a base like, let's say, lithium hydroxide. It's such a strong base, it's going to dissociate completely into its ions, which are the lithium cation and the hydroxide anion. So strong base and strong acid are denoted by irreversible arrows, not in equilibrium. Okay, good. Now let's move on from there. Again, some interesting tidbits here. I'll let you spend some time looking at that if you want. You can investigate why marble and limestone statues, which contain calcium carbonate, why they corrode with acid rain. Anyhow, I'm not going to ask you anything about that, I don't think. Anyhow, you might be wondering, how do we measure pH? Well, there's a few ways that we can measure pH in the lab. The easiest way is to use pH paper. And if any of you are taking the lab right now, you might have already done this, maybe, or it might be something that's planned for the future, is measuring pH using pH paper. Here we have a pH indicator scale, so this is using a dye, okay? You can even do that with cabbage juice. Anyhow, but you can see that these 2 examples here are really inexpensive ways to measure pH. You can also use what's called a pH meter. Now, Mr. Dion is not the world's expert in pH meters. I've used them many times in my life. But it says here that a pH meter can have a resolution up to the 1000th place, so that's pretty darn good. But the problem with pH meters is, number one, they're super expensive. You see that they cost $1,000. And another problem, and this is my personal experience, I don't know if, probably analytical chemists would disagree with me, but I always found that whenever I tried to use them, they're difficult to calibrate, and if they're not stored properly, they can give you incorrect readings. And again, Mr. Dion is not the world's expert in pH meters, but when I worked in industry, I used them, and I never liked them. Okay, I'd always trying to find a way to not do it, to not measure the pH, or find a cheaper, simpler way to measure it. You can also have these little portable pH meters here. You can see that somebody just stuck it right in the bottle top here, and they're able to measure the pH to the 100th place. Anyhow, But again, the pH meters, we do use them in the undergraduate labs from time to time, so they're useful for sure. Anyhow, well, let's move on to section 14.3, which deals with the relative strengths of acids and bases. Why is hydrochloric acid a strong acid, right? I told you that HCl is a strong acid. I see somebody says, is sulfuric acid ionic? No, absolutely not. Because to have an ionic compound, it has to be comprised of a metal and a non-metal, right? It's something from General Chemistry 1, right? An ionic compound has a metal and a non-metal in it. Sulfuric acid, hydrochloric acid, these are only comprised of non-metals, hydrogen, sulfur, oxygen, chlorine, okay? It's because they dissociate. Oh, the statue, part of the statue is ionic, yeah, for sure. Anyhow, what else? But why is something like HF, hydrofluoric acid? If you watch Breaking Bad, it's a little far-fetched when they use the hydrofluoric acid. They're throwing it around like it's candy. But why is hydrofluoric acid a weak acid? It's not a strong acid. Well, there's reasons for those kinds of things, okay? And we're going to talk about that a little bit now. And there's some rules that you're going to have to memorize, okay? So let's take a look here. It says the strength of an acid is measured how? By its ability to donate a proton to water, right? You guys remember the thing they used to do, making it rain? I don't know, maybe you're too young to remember that, making it rain, you know? I always think of an acid as something that can make it rain protons, right? The stronger the acid, the greater the ability the acid has to make it rain protons. And so if we have a strong acid, it's going to ionize completely, right? And I told you that already today, that we have an irreversible arrow for a strong acid. I told you that you have to have these acids memorized. I don't know why chloric acid is in here. I'll have to double check our textbook to be 100% sure about this, but maybe another textbook. I think that CHEM maybe uses chloric acid, right? Because this is perchloric acid, this is chloric acid. I'll go back and double check it for you though. Anyhow, but what about weak acids? Now there are many weak acids, you know, thousands of different weak acids. However, there are some that are going to come up so often in this class, you guys, there's just no way around it than to memorize them, right? Weak acids partially ionize in water. We use the equilibrium arrow. What are the weak acids? We have acetic acid here, right? This is acetic acid. You've already seen it 3-4 times in this class, right? Phosphoric acid, carbonic acid, nitrous acid. The ammonium ion is a weak acid, and hydrofluoric acid is also a weak acid. Okay, the strength of a weak acid depends on how far the equilibrium position lies to the right. Okay, so the more protons it can donate, the stronger it's going to be. Violet, you don't need an announcement. I just told you, okay? Right here. You need to memorize these and memorize those. Slide number, whatever, 30. Okay, let's get back to it. Okay, so again, the stronger the acid, the more the equilibrium is going to lie to this side, right? You have a strong acid, you have a stronger acid, so on and so forth. Okay, there we go. So with that in mind, if we think about this in terms of, you know, some people need a picture. A picture is worth 1,000 words, right? If you have a strong acid, it says for the hydrolysis of a weak acid, HA in water, what's your equilibrium constant going to be? Your Ka, right? You have HA, your acid, plus water, which is a liquid. It's going to be in equilibrium with the hydronium, plus the conjugate base. All of these are aqueous, right? So your Ka is going to be equal to the concentration of each of the products. The product of the concentration of each of the products divided by the concentration of the acid. So what about that Ka? What about that number? Well, let's think about it. If you have a strong acid, it's going to dissociate completely, as is shown here. I'm trying to get rid of this so you can see the whole dang slide. Come on. There you go. If I have a strong acid, it's going to dissociate completely, right? At the end, what have I got? Where it says final amounts? I've only got H plus and A minus. I've got no HA left over. But if you look at a weak acid, you start out with the acid. What have you got at the end? You've got some of the hydronium, right? The proton. You've got some of the conjugate base, but you've got a lot of the weak acid left over, right? It says only a small fraction of the molecules are going to dissociate, right? So it says here that an acid with a high Ka is going to be stronger than an acid with a low Ka. Why? Because the stronger the acid, the greater the concentration of the hydronium and the conjugate base will be, okay? So you have to understand higher Ka, stronger acid, lower Ka, weaker acid, right? There we go. Now, where do you get the Kas for all these different acids that we've looked at? Well, you'll see them in tabular form. So here's the Ka values for a few different monoprotic acids. Okay, got a whole smattering of them here. If we compare some of these, let's say we try to compare, I don't know, let's pick hydrofluoric acid and hydrocyanic acid. Could anybody tell me which one of these is a stronger acid, HF or HCN? Yeah, absolutely, right? Because the greater the Ka, right, as the Ka increases, we have, we'll do it over here, stronger acid, not a strong acid. None of these are strong acids, but, and then we have weaker acid. Again, the greater the Ka. Why? Because Ka is going to be equal to the concentration of hydronium times the conjugate base divided by the initial the concentration of the weak acid that's left over. Okay? Let me ask you guys a question. Do you know the difference between, and this is general chemistry, okay? So this is chemistry 1401. Do you know the difference between HCl here and HCl here? This is a little nomenclature quiz. Could anybody tell me the difference between these two, HCl gas and HCl that's aqueous? It would be something you would have learned. Aqueous means it's an acid. Yeah. So aqueous, I mean, HCl gas is still an acid too. Yeah. But what, how would you name this? What would you call this? Okay. HCl gas is called hydrogen chloride. Okay. Because HCl is a gas when it's pure. If you take hydrogen chloride and you bubble it through water, you get aqueous HCl, right? But that is hydrofluoric acid. Okay, so there's a big difference in the name between HCl gas and HCl aqueous. So that tells you that all of these are aqueous, right? Because they all have acid in the name, except for this one here, which is just a hydrated ion. But anyhow, so say, for example, you have HCN, hydrocyanic acid, that tells you that it's aqueous. If you have HCN like this, that's hydrogen cyanide, which is what they would use in the gas chamber in California when they used to use that. They just take potassium cyanide or probably potassium cyanide pellets and put it on top of a bucket of hot sulfuric acid and just pull a string, and dump it in there. And there you go. You go it the hard way. All right, anyhow, enough about that. So with that in mind, let's take a look at question number 18. It says, write the acid dissociation reaction in water and the expression of Ka for the following acids. Rank the acids in order of increasing strength. Well, in order for us to tell the difference between the strengths of each of these acids, we could turn back here. We have nitrous acid, which is right, I'll do a different color, which is here, and we have the ammonium ion here. So I'll write those down here. So let me write that down. So for the ammonium ion, we have the Ka, or maybe I didn't write that. Yeah, we have a Ka, which is equal to, what was it again? 5.6 times 10 to the negative 10. Then for the nitrous acid, we had a Ka, which is equal to 4.0 times 10 to the negative 4. Okay, could anybody tell me which one of these three is the strongest acid? Could anybody tell me which one of these three is the strongest acid? Yeah, I like the way you think. Good. It's HClO4, right? Because HClO4 was in the list of strong acids. These two are not in the list of strong acids, so perchloric acid is definitely the strongest, HClO4. Okay, then if I compare the relative Kas of the two of them, the weakest acid is going to be the one with the lower Ka, right? So the weaker acid is going to be the ammonium ion, and then nitrous acid, HNO2, is going to be somewhere in the middle. Let's just write the dissociation reaction with water with, let's say, ammonium. Let's do A and C, right? I keep doing A and C. So if we do A, we have the ammonium ion, which is aqueous. We put it in water. Since it's a weak acid, we write an equilibrium arrow. It's going to donate some of its protons to form a hydronium ion, and you're going to be left over with ammonia. If we try the same thing with the perchloric acid, HClO4, it's aqueous. If we put that in water, okay, it's going to be, we're going to produce hydronium and the perchlorate ion. Can anybody tell me where my mistake is here? I made a mistake in this
situation. It should not be reversible.
Heck, diggity darn. I don't know who said it, but you're 100% right. Okay? Perfect. Thanks for answering my question. Good. It's an irreversible arrow. Why? Because it's a strong acid. Now, there's a question down here at the bottom that says, why are there no Ka values listed for strong acids? Okay? Why isn't there a Ka value? Because if you had a strong acid, let me do it in a different color. Your Ka is equal to the concentration of hydronium multiplied by the concentration of the conjugate base divided by HA. Well, if you've only got your hydronium in your conjugate base and you've got nothing in the denominator, when you have a 0 in the denominator, try putting that in your calculator. 1 divided by 0. Uh-oh, my calculator broke, right? You get an error, okay? So there's no such thing. You wouldn't get a value because it dissociates completely. It says here, chlorous acid has a fairly high Ka value. Can it be defined as a strong acid? The answer is no, because it does have a Ka value. It might be high, but it's definitely not as high as a strong acid. And so you can't define it as a strong acid. There you go. So does that clear things up a little bit about the strength of acids? Somebody asked, do we need to memorize the Ka chart? Only Mackenzie needs to memorize. I'm teasing, okay? No, you don't have to memorize the values of Kas. I'll tell you what, though, since we were talking about organic chemistry a little bit this morning, when you take organic chemistry, you'll look at the minus log of the Ka, which is a pKa, right? Same thing as pH. pKa is equal to minus log of the Ka value. In organic chemistry, you have to memorize a bunch of pKa values. But again, in this class, you do not have to do that, okay? All right, let's talk about bases, and I'll speed up here because I'm sure you kind of follow the concept by now. The strength of a base, how strong is a base? Well, how well is it, or how good is it at accepting protons, right? Again, we said a strong base dissociates completely in water or ionizes completely in water. Group 1A, 2A, I went over what the strong bases are, the 6 strong bases that you have to know, 100% dissociation. Whereas a weak base is only going to partially ionize in water. And the reason I'm going faster now is because it's the same rationale that we saw with acids, right? A strong acid dissociated completely. Strong base dissociates completely. A weak acid dissociated partially. A weak base ionizes partially, right? There you go, my friends. Nothing more. What about a Kb? How would I calculate a Kb? If you have a base and you put it in water and you wanted to calculate a Kb for that base, look, it would be Kb is equal to concentration of hydroxide multiplied by the concentration of the conjugate acid, so OH minus times the concentration of the conjugate acid divided by the concentration of the base. Look, I'll prove it to you. Watch. Copy. Show my copy-paste skills. And look. There you go. It's the same formula that we see there. Okay? So it says here, for the hydrolysis of a weak base, the equilibrium constant expression shown here, same rationale that we saw with acids. The greater the Kb value, stronger base. Lower Kb value, weaker base. Nothing more than that. So what have we got so far out of Ka and Kb? Right, let's think about it really hard. We said the higher the Ka value, stronger acid, lower Ka value, weaker acid, higher Kb value, stronger base, lower Kb value, weaker base. Now you might be wondering, why are you repeating that to me, Mr. Dion? I already knew that. That's pretty easy. Well, where we're going is we want to look at the relationship between Ka and Kb. I'm going to show you what the relationship is, and you're going to find it hopefully pretty interesting. Before we do, I want to mention electrolytes a little bit. This is a topic I know that many of you were my students in General Chemistry 1, and I remember we talked about electrolytes in this class, and later on we'll talk about electricity and electrochemistry and all that stuff. Not today, but if you take a strong acid and you put it in a solution, and then you run a current through that solution, and that's what's going on over here. Okay, this beaker on the left has this is a strong acid that's in here. You can't even see what I wrote. This is a strong acid. Okay, it allows for the conduction of electricity, so it allows electrons to flow through the circuit, and therefore it lights up the light bulb. If you have a weak acid, however, since there's a lot less ions, it doesn't allow the electrons to move or flow, and so it's only going to partially allow electricity to be conducted between the electrodes down here. Anyhow, the take-home message, I mean, this might be worth the value of one multiple choice question on your next exam, would be something like this. Strong acid is going to, or strong base or strong acid is going to be a strong electrolyte. Weak acid, weak base is going to be a weak electrolyte. In fact, you know what? I've taught chemistry for nurses, for nursing students. I've taught it many, many times. And there's a little experiment that we do in that class where we take something like hydrochloric acid, which is a strong acid, and we'll start it with a, maybe a 2.0 molar solution of HCl, and it lights up the light bulb perfectly. But what happens is we start to decrease the concentration, we'll lower it down to like 0.001 molar, and then it won't light up the light bulb at all. So it's not just about the strength of the acid, it's also about the amount of ions, in the solution, okay? Anyhow, just something to think about, and I thought you might find that interesting, so I threw that in here. Okay, all right, I have a lot of students with inquiring minds, so let's go and try question number 19. It's in the same vein as the last question. We're looking at some Kb values here. They're all written for me this time. It says, write the base ionization reaction in water in Kb expression for each. Rank the bases in order of increasing strength. Well, again, the higher the Kb, the stronger the base. So we can clearly see that out of these three, ammonia is going to be the strongest base. It's got the highest Kb. And the perchlorate ion is going to be the weakest base. It's got the lowest Kb, and then the nitrite ion is going to be somewhere in the middle. Let's start by writing the ionization expression for ammonia. So if we have ammonia, okay, and we put that in water, right? If ammonia behaves as a base, what's it going to do? It's going to take a proton from the water, right? A base is a proton acceptor. Okay, so we're going to end up with the ammonium ion plus we're going to end up with hydroxide. So if we wanted to write the Kb, it would be Kb is equal to the concentration of the ammonium ion times the concentration of hydroxide divided by the concentration of ammonia. Let's try C, just for fun. So this was A, and if we want to try C, we have the perchlorate ion. We put it in water. It behaves as a base. Not a strong base, that's for sure, with a Kb that's that low. Find out where I was. There we go. Anyhow, so we end up with perchloric acid, and we end up with hydroxide. And so our Kb would be equal to the concentration of the perchloric acid multiplied by the concentration of hydroxide divided by the concentration of the perchlorate ion. It says here, do you notice any trends between the strengths of conjugate pairs? So conjugate base and conjugate acid. Right, look, if this is your base, and this is your conjugate acid, and if this is your base, and if this is your conjugate acid, well, you see that ammonia is a stronger base than perchlorate, isn't it? Well, what about the strengths of their conjugate acids? We know that perchloric acid is a strong acid, right? Ammonium is a weak acid. What's the conclusion that we can draw? The stronger the base, the weaker the conjugate acid, and the weaker the base, the stronger the conjugate acid. Okay, so if you didn't follow me on that, you'd say the stronger the acid, we get a weaker conjugate base, and the weaker the acid, the stronger the conjugate base. Okay? Very important that you understand this right here. Stronger acids produce weaker conjugate bases, and weaker acids produce stronger conjugate bases. Okay? Again, Violet, if you need a list, this is the list of the 6 strong acids and the 6 strong bases. Memorize this list. And let's get back to the relative strengths of these conjugate pairs. Now, if you didn't follow me 100% on the conclusion that we drew from the last question, I'm going to go over it a little bit quicker here. Let's think about it for a second. It says, if the Ka for an acid dissociation is large, that means you get a strong acid. It's going to favor the products. The acid donates a lot of base. But again, if it's a strong acid and the reaction is irreversible, then that means the conjugate base must be weak because this reaction is not happening, right? So that tells you, again, strong acid gives you a weak conjugate base. Let's look over here. What if we have a weak acid? Well, if a weak acid only partially dissociates, that tells you that the reverse reaction occurs even more than the forward reaction. And therefore, that tells you that the base, the conjugate base, is going to be strong. So therefore, if you have a weak acid, you have a strong conjugate base. All right, there we go. If you look at this chart that I have on the side here, it's kind of hard to see, but you see that the relationship between acid and base strength. If you've got a strong acid, you've got a weak conjugate base. If you have a weak acid, you've got a strong conjugate base. Okay? That's a very important concept. Here's a figure that comes straight out of our textbook. Let's take a look. If you have a strong acid like hydronium, okay? There's the hydronium ion right here. What's the conjugate base? It's water. Water's not a strong base. Right? Not at all. What if you go up to something like water? Do you consider water a strong acid? Because I certainly don't. I'm not like, I better put the gloves on. I'm going to be handling some water today. I don't want to burn my hands. No, I wash my hands with water. Okay? So if I have water, which is a weak acid, that means it's conjugate base. Ooh, hydroxide, that's very strong, right? So I've gone over the same concept 4 times already today, but I want to make sure that you understand that concept, okay? Strong acid, weak conjugate base, weak acid, strong conjugate base. All right, there we go. Relative strengths of acids and bases, and let's get into why is one acid a strong acid, why is another acid a strong acid, and we have to look at the bond between an atom and the proton or the hydrogen atom that is acidic, right? Because if you think about HCl, let's go back to general chemistry, right? I keep going back there, don't I? Think about HCl and you look at the Lewis structure. What the hell would make this a good acid? It's the ability of this bond to break so that I can form H+. That's my acid, right? That gets solvated in the water to form hydronium. But that's the whole idea, is I've got to examine this bond. Okay, how strong is that bond? The weaker it is, the better it's going to be at donating protons, making it rain protons. Okay, So it says here, the strength of the acid is defined by the ability for that stinking bond to break. What if we look at hydrohalic acid? So you start with the halogens, right? This is group 7A. You go from fluorine down to chlorine, down to bromine, down to iodine. You can make an acid out of all those. Hydrofluoric acid, hydrochloric, hydrobromic, hydroiodic acid. Now, I told you that hydrofluoric acid was a weak acid, and I told you that the other three were stronger. Well, why would hydrofluoric be weak and the other ones be strong? Well, it's got to do with the size of the halogen, okay? As the size of the halogen decreases, we get a stronger and a shorter, smaller bond. Okay, so what does that mean? Since the size increases going down the group, that tells you that hydroiodic acid is going to be the strongest because it's got the longest and weakest bond. And then when we go this way, right, since size decreases, well, since the hydrogen fluorine bond is so small, so short, it's going to be really strong and it doesn't break easily. Okay, that's a rule that you've got to have memorized. Everybody that's hearing the sound of my voice has to know that rule. You can see how this would lend itself to a multiple choice question very easily for Mr. Dion. Okay, I put all four of these. Which one's weak? Okay, there you go. You know, what's the rationale? Is it size? Yes, based off of the size of the halogen. Okay, what about oxyacid? We see all kinds of acids like, you think about, you go perchloric acid, right? Then you go down to chloric acid. Then you go down to chlorous acid. Then you go down to hypochlorous acid. Then you could have hypobromous acid, right? You know, hypoiodous acid, right? What about all these oxyacids? There's a whole holy host of them. Yeah, there's a couple of rules that you need to know for the oxyacids. It says the oxyacids all have oxygen-hydrogen bonds. They all do. So you can't really go off of bond length. Instead, what we go off of is bond polarity. Okay, so we look at the strength of the dipole. Okay, and if you're like, oh no, do I have to draw a bunch of Lewis structures and analyze them and blah blah blah? No, I can make it much simpler than that. Here you go. It says here if the number of oxygens bonded to the central atom is identical, then the acid strength is just determined by electronegativity. Okay, so since chlorine is more electronegative than an iodine, hypochlorous acid is going to be stronger. Let's think about it. If you're like, well, why would that be, Mr. D? I don't understand. Well, look, what would you have left over? You'd have a proton after that dissociates, plus you'd have the hypochlorite ion. It has a negative charge. Since chlorine is more electronegative, overall, since chlorine is more electronegative, it's going to better stabilize that negative charge, right? If you have hypoiodous acid, you have the proton, which doesn't remain changed. But since iodine is less electronegative, it's not going to be as good at stabilizing that negative charge. What if you have these? So this is the same rationale here because all these have the same number of oxygen. Sorry, I wanted to get on to, where's my next one here? Yeah, here we go. So what if you have the central atom is the same? It's going to, the strength of the acid is just going to be determined off of the number of oxygens. Okay, remember, when it comes to electronegativity, you have nitrogen, oxygen, fluorine, right? Bromine. Okay, you know that fluorine is the most electronegative element in the periodic table. Well, oxygen takes the silver medal, right? It's the second most electronegative element in the periodic table. And so what happens is, if you compare a nitrate ion to a nitrite ion, since there's more oxygens here and oxygen is electronegative, it means the conjugate base of nitric acid is going to be more stable than the conjugate base of nitrous acid, just off of the ability of all those oxygens to suck that negative density, electron density away. Okay? Give me a thumbs up if you follow me on the concept. It's probably simpler than I'm making it out to be, maybe over explaining it, but I also can't see your faces. So it's hard to know when my students are like, yup, move on, Mr. Dion, or I'm confused, you know? All right, thanks, Joey. Good. Well, look, it isn't supposed to be a difficult question, number 20, and I'm not going to bother drawing the Lewis structures because that's something that you would have done in Gen Chem One, if you want to look at the Lewis structures of these 4 acids, just look at the solutions that I have posted to Canvas. Let's do A. If you have sulfuric acid, H2SO4, versus sulfurous acid, which one of these is stronger? Which one will be a stronger acid? Not a trick question. Yeah, thanks. Exactly. It's going to be sulfuric acid. Why? Because more oxygens, right? They're going to pull that electron density away, stabilize that conjugate base. What if we look at B? We've got chloric acid and bromic acid. Which one would be stronger? There we go. Yeah, it's going to be HClO3, right? Why? Because chlorine is more electronegative than bromine, like that. All right, perfect. So strengths of acids, we always cover this in any general chemistry 2 class. It's just something that we have to do before we really get into looking at ice tables and stuff. So we covered that question. Again, this is a figure that comes straight out of our textbook and shows the same thing, that the stronger the acid, right? If you have a strong acid, you're going to have a weak conjugate base. If you have something that's a really weak acid, like let's pick water, for example, it's going to have a strong conjugate base. Okay? Anyhow, and then you can see some really strong bases that are over here. All right. So one thing that I can encourage you with, okay, Mr. Dion likes to encourage his students, not discourage them. One thing that you'll realize in this class is if you put in the work in general chemistry 2 and you do all the practice problems and everything, go through the book in detail, look at all the practice that you can, you're going to get more and more used to seeing acids and bases and just knowing which one is strong, which one is weak. Okay. Eventually it'll kind of become like old hat to you. Like, yeah, I know the rules. It's like organic chemistry. We see some of the same topics so many times that seem complicated at first, but once you've seen it 1,000 times, wow, it starts to sink in, even for people who might find it more difficult. Okay. Well, we've got 2 hours left in the lecture, and I'm just getting warmed up here. So let's talk about what's called percent ionization. This is just another definition that you need to know. So let's say you have a weak acid. You put it in water, it dissociates to give you hydronium and the conjugate base. Well, we defined Kb already, but the percent ionization is this, is where we have the concentration of the hydronium at equilibrium divided by the initial concentration of the acid. So that's what the 0 means. So initial concentration, and this is at equilibrium. Okay. Now you might be wondering, isn't this just like Ka? Well, unlike Ka, the percent ionization of a weak acid is going to vary with the initial concentration, right? And typically, it's going to decrease as the concentration increases. All right. So again, it's different than Ka because we can start with different initial concentrations, right? What if you have a 1 molar solution? What if you have a 0.1 or a 0.01 molar solution? So again, percent ionization, it's a formula that you need to know, and we're going to use it in several problems throughout the course. Well, before we get into some more problem solving, which I want to do in just a few slides, I want to take a look at the relationship between Ka and Kb. Remember I told you we were going to look at that? Okay. Let's go for it here. It says, consider the case when you have an acid and put it in water. Okay. Nothing new to anybody here. You write out the equilibrium expression. Okay. Good enough. But what about that conjugate base? All right. We know that the conjugate base can do the reverse reaction, and it could also, and this is something new, okay? Not repeating myself here. look at this closely. It says, since you've got some conjugate base in solution, it could also react with water molecules. Why couldn't it? There's no reason why it can't. It's a base. Okay. So, and if you're going, well, Mr. Dion, doesn't this represent everything that happens to the weak acid when it's in solution? No, it doesn't. Okay. It represents the dissociation of the weak acid, sure. But what I'm telling you now is something new. I'm saying, consider this, you guys. What would happen if the conjugate base reacted with water? Well, why couldn't it do that? There's no reason why it can't do this. Okay. And if we wrote out an equilibrium expression, it would look like this, like KB right here. Everybody here could, solve for that. I could have asked you that question on the last exam. Okay, good. I follow you on the first two parts, Mr. Dion. I'm with you there. Well, what about water? We know that water undergoes auto-ionization, right? We looked at this in the last lecture. I taught you that Kw is equal to the concentration of hydronium times the concentration of hydroxide. Well, what's the relationship between these two equations and this equation right here? I'm not expecting you to figure it out, instantly, but if I show you where it comes from, okay, you've got in solution, you've got your acid, the conjugate base, you've got hydronium. I showed you why you have hydroxide, right? I told you that's something brand new. That's for today, brand new. You've got water in there. It's a soup. Okay, you've got all of these players in here. But their concentrations have to satisfy the Ka expression, the Kb expression, and Kw all at the same time. So here's the answer. If you multiply the Ka times the Kb, look what happens. Concentration of the acid cancels, and the concentration of the conjugate base cancels. That gives you this expression right here. The Kw is equal to Ka times Kb. Now you can imagine, you're like, oh boy, this looks interesting to me, Mr. Dion. It should. And you need to have this equation memorized. Now you're going to use it so many times that it will be burned in your brain by the time you get to the next exam. But that's a pretty interesting relationship, right? We spent a lot of time talking about Ka, talking about Kbs, okay? And now we know that the product is going to be equal to Kw. Well, since it's the product of the Ka and the Kb is equal to Kw, that tells us that if Ka is a really big number, Kb must be a small number. If Kb is a really big number, Ka must be a small number, right? We know that. That goes right back to what we talked about today. See, it's like a episode of Seinfeld, right? Everything all comes together in the end. The stronger the acid, the weaker its conjugate base. The stronger the base, the weaker its conjugate acid, right? You're like, I'm still not following you, Mr. Dion. Watch. What did we say before? We said the stronger the base, the bigger its Kb. Okay. Well, if the Kb is really high, that tells you that the Ka of the conjugate acid must be really low, right? This would be strong. This would be weak. Look, I don't mean to sound like exasperated or anything, but I don't know how I could explain it any more than that, okay? Give me a thumbs up if you're with me on that idea. On all the concepts that we've looked at with Ka, Kb, this expression. Is anybody with me? Yeah. All right. Thanks, Ben. All right. Great. Ben, Joel, Katie, Shannon, thanks a million. I appreciate it. That's good. Okay. And again, I never said it was simple. Okay. Mr. Dion never said anything like that. Whoa. I never said that. I just said you got to understand it, and I want you to understand it. Because, as I tell you all the time, this class is a lot more exciting. It's a lot more interesting. It's a lot easier to sit down and study it when you understand what the heck is going on, right? A lot more enjoyable. Let's take a look at question number 21. It says here, identify the conjugate of each of the following compounds and calculate its Ka or Kb. Explain the relative sizes of Ka and Kb. Let's do it. Well, if we have HCN, okay, which is hydrocyanic acid, it's an acid. It's Ka, it's another clue that it's an acid. They're giving it an equilibrium constant for the dissociation of an acid. That's what the A stands for. Okay, its Ka is equal to 6.2 times 10 to the negative 10. Is that what it is? Yeah. Now, its conjugate base is going to be cyanide, right? If we lose a proton, we end up with cyanide. So what's the Kb going to be equal to? Kb is going to be equal to something. Well, what did I tell you last time? I said that Kw is equal to Ka times Kb. And at 25 degrees Celsius, it doesn't say here, but we'll just assume all these are at 25 degrees Celsius, is equal to 1.0 times 10 to the negative 14. Therefore, my Kb is going to be equal to Kw divided by Ka. 1.0 times 10 to the negative 14. What have we got? 14 divided by 6.2 times 10 to the negative 10. Shoot. Anyhow, it's going to be equal to 1.6 times 10 to the negative 6, which is equal to my Kb. There's my Kb. There's my Ka. Now, if we think about the sizes of these Kas and these Kbs, the Kb is bigger than the Ka. What does that tell you? That tells you that the conjugate is a stronger, or the HCN is a weak acid, so it's got a strong conjugate base. Okay? I'm trying to think of the easiest way. So weak acid, therefore strong conjugate base. Let's try one more and we'll move on. The next one is HF, or let's try the ammonia. Yeah, let's try that. So we have this B, we have ammonia, we have our Kb, which is equal to 1.8 times 10 to the negative 5. Could anybody tell me what the conjugate of ammonia would be? What would its conjugate be based off of the information that's given here? The conjugate of ammonia, yeah, it's ammonium, right? NH4. Right here, we're going to add H plus. If you're saying, why did you lose hydrogen here and gain it here? Well, because here they gave me a Ka. Acids lose protons. Here they've given me a Kb. Bases accept protons. So my conjugate is going to be the ammonium ion. So its Ka is going to be equal to 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. And I get 5.6 times 10 to the negative 10 is being equal to my Ka. And so it tells us that if we compare the Ka of HCN versus ammonia, what do you see? We see a difference in size. Okay, if we go back, all the way back, where am I here? So I'm going to show you. Shoot. Wait. Where are they? If I compare my HCN, right, and my ammonium ion, you see that HCN is a stronger acid because it's got a bigger Ka. That's it. So what did that tell you about the conjugate bases? It tells me that cyanide, Cn minus, must be a weaker base than ammonia. Let's go back here. There we go. So therefore, Cn minus is a weaker, weaker base than ammonia. Okay, so just by examining Kas, Kbs, Kws, we can find all kinds of interesting information. All right. Well, now we're going to switch gears, and now we're going to shift into something that's a little bit more difficult. Okay, I don't like to use the word difficult. I'm not using that word to try to intimidate you. Maybe just to get you to pay closer attention. It's going to end up being a little more difficult here. Okay, so if we go and we think about a 1 molar hydrochloric acid solution, how much HCl is left over? Right? How much HCl would there be in a 1 molar hydrochloric acid solution? Well, the answer is none. Okay. If you're thinking, what? Come on, Mr. Dion, you just told me I have a 1 molar solution of HCl. Why is there no 1 molar HCl? Because I told you that HCl dissociates completely into, right, its ion. So there's going to be none of this left over at equilibrium, right? Now, with a weaker acid, it gets more difficult because if you have a 1 molar solution of a weaker acid, how much HF? Well, that depends on the Ka, doesn't it? So you'd have to know the Ka in order to determine how much of each component is present. The acid, the base, conjugate base, sorry, so on and so forth. So again, in a strong acid, there's almost none of the original compound in the solution. So the molarity of an acid or a base, when you see a bottle in the lab and it says 1 molar HCl, okay, it indicates the concentration of acid or base before ionization has occurred. It doesn't tell you what's actually present in equilibrium. Okay, now that might not be simple, and I never said it was simple. I said it's getting more difficult now. Okay, so in order for us to understand what the heck is going on here, okay, we've got to be able to identify everything that's present in the soup, right? I said it's a soup, and we want to look at their relative amounts. All right. So it says here, in an acidic or basic solution, you're going to have appreciable amounts of compounds contributed by the ionization of an acid and a base in water. Negligible amounts of hydronium and hydroxide from the autoionization. And we usually ignore the concentration of the hydronium or hydroxide when we're dealing with an acid or a base solution because they're often present in such small amounts. So, again, I'm repeating myself. Strong acids ionize completely. Here are the strong acids. Again, I got to double check our book about chloric acid. I'll come back to you with that on Monday. And then we went over the strong bases. So with all of that information in mind, now we're going to tackle these three problems, 22, 23, 24. Question 22. It says, calculate the pH and equilibrium concentration of all species present in a 0.020 molar solution of HCl at 25 degrees Celsius. Use an ice table or an ice chart to show the dissociation of the HCl in solution. So follow me here. I'm not going to take a lot of time on this one because it's a strong acid. We have our HCl. We know it's a strong acid, so we know that when we put it in water, it's going to dissociate completely. Right? 100% dissociation to give us hydronium plus the chloride. So initially, we're starting out with 0.020 molar. Remember, I said that when we're given a concentration, it represents the concentration of the acid before it's reached equilibrium. So initially, we only have the strong acid. We have none of these. Then we have a change. Since this does 100% dissociation, we're going to lose all of this. And we're going to gain 0.020 molar hydronium and 0.020 molar chloride. So at equilibrium, we don't have any HCl. Again, why? Because it's a strong acid. But we're going to have 0.020 molar hydronium and 0.020 molar chloride. It's asking us to determine the pH. My pH is going to be equal to minus log of 0.020, 2 sig figs. Therefore, I report my pH to 2 decimal places. You take that, punch it in your calculator, you take 0.02, and you take the logarithm of it, you get 1.70. So there's my pH. I've also got the concentration of my hydronium, which I've already solved, is 0.020 molar. Now, if I want to calculate the concentration of the hydroxide, okay, that's going to be present in solution, right? Because we know there's going to be a little bit of hydroxide in solution. If you're going, like, where's that going to come from, Mr. Dion? Remember what I told you. The conjugate base could react with water, couldn't it? To produce HCl plus hydroxide. We're not going to have a lot of this because since hydrochloric acid is such a strong acid, this is a very weak base. Right? It's an extremely weak base. So we're probably not going to have a lot of hydroxide, but let's figure out how much we've got. Okay, so the amount of hydroxide is going to be equal to the Kw divided by the concentration of hydronium. 1.0 times 10 to the negative 14 divided by 0.020. That means my concentration of hydroxide is equal to 1 times 10 to the negative 14 divided by 0.02, and you get 5.0 times 10 to the negative 13 molar, right? There's not much. That's a very small concentration. Also, I forgot to include the concentration of the chloride, which is going to be equal to the concentration of the hydronium. So we've got the concentration of the HCl, which is 0 molar. We've got the concentration of both of these, which is 0.020 molar. We've got the pH, and we also determined what the concentration of the hydroxide is, even though there's very, very little of it in the solution. Let's move on to question 23, which gets a little more interesting. It's still dealing with nitrous acid, which is a strong acid. It says if you have 25 milliliters of nitric acid, did I say nitrous acid? Because I meant nitric acid. If you have 25 milliliters of nitrous acid, it's got a pH of 1.50 at 25 degrees Celsius. What mass of nitric acid was used to prepare the solution? If you dilute it to a volume of 300 milliliters, what's the new pH? Right, if we're diluting it, the concentration of the H plus is going to decrease. Well, first, let's start out by determining the concentration of the hydronium. Sorry, I'm getting tired here. Anyhow, how would we do that? Well, let's think about it. Nitric acid is a strong acid. Okay, you take it and you put it in water. If it's strong, it's going to 100% dissociate into hydronium ions and the nitrate ion. So based off of what we learned, since this is going to dissociate completely, right? If we want to know the concentration of the hydronium that we have at equilibrium, it's going to be equal to 10 to the power of the negative pH. Right? Again, because it's a strong acid, the concentration of this initially is going to be equal to the concentration of that at equilibrium. So we say that the concentration of the hydronium at equilibrium is equal to 10 to the negative 1.50. I've got 2 decimal places. I report my concentration of hydronium to 2 decimal places, and I get 0.032 molar. Let me just double check that quickly on the calculator. By the way, if you guys don't mind checking my calculations, yeah, looks good. Okay, so there's my concentration of hydronium. Remember that that's also going to equal the initial concentration of my nitric acid is going to be equal to 0.032 molar. Right? I didn't complete the whole ice table. I'm taking it, I'm going to assume that you understand again that this is 100% dissociation. So this is what I started out initially, and this is what I have at equilibrium. So they're asking you what mass of nitric acid was used to make this solution. What kind of solution do I have? Now it's a general chemistry 1 problem. You've got 25 milliliters of a 0.032 molar solution, right? Gen Chem 1. Let's work it out. We've got this many milliliters. Let's convert it to liters. So 1, 2, 3. So we have 0.02500 liters. So we have 0.02500 liters of our nitric acid multiplied by the concentration, which is 0.032 moles of HNO3 for every 1 liter of HNO3. Our volume of HNO3 is going to cancel. Now, if I want to know the mass, I need to know the molar mass of nitric acid. I went ahead and looked it up instead of calculating it myself. I was too lazy. It's 63.01 grams per mole. But I know you all know how to do that. So I have 63.01 grams of nitric acid and 1 mole of nitric acid. And look at this. These cancel, and I end up with a mass of nitric acid, and I get a mass of 0.050 grams of HNO3. So that's the mass of nitric acid that I needed. Can anybody tell me what to do in the second part? The second part just asks me, if you dilute it to 300 milliliters, what's the new pH? Did anybody get an idea what you do here? You can unmute your mic or type it in the chat. The key word is diluted. Does anybody remember the formula for the dilution? Yeah, thanks, Joel. Who remembers what the equation was for dilution? Yeah, M1V1 is equal to M2V2, or you can call it C1V1 is equal to C2V2. Yeah, great, awesome. This is great. So when we dilute it, okay, I'll switch over to a green pen. Maybe I'll use black, probably easier to see. So for dilution, my students told me it's M1 times V1 is equal to M2 times V2. We're solving for M2. We want to know the new concentration. It's going to be M1 times V1 divided by V2. So we have our initial concentration, which was 0.032 molar times 25.00 milliliters divided by 300 milliliters. There can only be 2 sig figs in the concentration. And what do we get? So we take 0.032 times 25 divided by 300. And you get 0.0027 molar. Okay? Again, it's a strong acid. So this is going to be equal to the concentration of the nitric acid before it ionizes, and it's also going to be equal to the concentration of hydronium because it undergoes 100% ionization. So the new pH is going to be equal to the negative log of, was it 0.0027? So I take the, oops, crap, press the wrong button. 0.027 log. So it should be 2.57. pH is 2.57. There we go. Give me a thumbs up if you follow me on that one. Chuck, anybody with me? I told you it was getting a little more complicated. No, we did that. Did all this. Yeah, we did this one. We did this one. And this is where I wanted to go. So good. Everything's working out. And I wanted to get to this as being our last problem for the day. And I don't know if we're going to have time to solve the whole dang thing. So let me just stop there. Talk to my students for a sec.